Good afternoon. Welcome to the workshop from LINDO Systems on adding optimization to your large, complex what-if Excel models. Let's first have a general word from our sponsor. LINDO has 3 to 4 products, depending upon how you count them. Underneath all of them is the LINDO API optimization engine. What's best, the main topic today, is an add-in for Excel that allows you to find optimal solutions to what-if models in Excel. That's where the name What's Best comes from, namely, why ask what if when you can get what's best? We also have an algebraic modeling language front-end, LINGO. It allows you to formulate your planning models in essentially algebraic format. Finally, we can help users develop their own customized planning systems built on top of either LINDO API, LINGO, or What's Best. Each of our products has a callable interface. For What's Best, the callable interface is VBA. For LINGO and the LINDO API, there are interfaces for all popular languages such as C, C++, Python, R, etc. The most typical customized applications are things like supply chain management models, routing problems of various sorts, including scheduling, sequencing, and scheduling, cutting stock problems in the metals and paper industries, and financial planning models in the finance industries. In terms of more specific capabilities, I think we have perhaps the most comprehensive, easy-to-use optimization solver engine that it solves problems along the entire spectrum. So large linear programs are the basic feature, but you can have quadratic constraints or objectives, and they can be handled. And the quadratic constraints need not be convex. We have a global solver which can handle non-convex problems and still find guaranteed global optima for it. And more general than quadratic, we can handle conic constraints and even semi-definite constraints. And so we'll talk later about some financial covariance estimation problems for which the capability of handling semi-definiteness constraints is a useful feature. Also, we have some very powerful features for handling randomness or stochastic features in a model where you're not sure what the demands are going to be, or you're not sure what the prices are going to be. And you can have integer variables anywhere in nonlinear programs, quadratic programs, non-convex programs. You can use them anywhere. LINGO and What's Best are built on top of that solver engine, and they have all of the capabilities that are described and associated with the LINDO API. So in terms of what we'll be covering in the presentation today, there's a half a dozen of topics we'll cover, and here's a quick pass through them. We'll start out with piecewise linear cost functions, and these sorts of things arise in, say, purchasing or power generation and engineering design problems, perchance. So the basic idea is you don't have a well-defined mathematical function describing what's going on, but rather you have a table of what's going on. So if you're purchasing, your suppliers may give you a discount table and saying, if your purchases fall within this range, here is what the discount will be. If you buy a little bit more, the discount will be a little bit steeper, things like that. Somewhat related to those ideas, we'll talk about a very specific thing related to engineering design, heat exchanger modeling. We've got some special features in the solver and in What's Best in LINGO that help simplify the modeling of those features. We'll say a little bit about nonlinear network flows, and there's some special features that we have in What's Best in LINGO for modeling nonlinear flows in a network. There's a function called the sine power function, which is useful in those situations. If you're interested in finance kinds of applications, we'll be talking about risk and covariance matrices. These are arise when you're looking at Markowitz portfolios. They also arise in petroleum if you're interested in nonlinear blending, where Say if you want to approximate the octane and you're willing to use a quadratic approximation, you can do that quite easily in either What's Best or LINGO. And then estimating valid covariance matrices. This is where the semi-definiteness constraint will come in to help estimate good covariance matrices. Another topic we'll talk about is representing uncertainty, so-called multi-stage decisions under uncertainty, where we don't know what the demand will be this coming season, or even what the prices might be. We have to make some decisions now, nevertheless, in preparation for that. And then once we see what the demand is, once we see what the prices are, we then have to do as best we can, making reparations, trying to recover from what happened. And related to uncertainty, we'll illustrate some features related to sensitivity analysis, so-called K-best solutions. And then finally, the final topic we'll talk about is LINGO models in Excel. So those of you who are familiar with developing large models in Excel, you're aware that there is this problem of arthritis, that as the Excel model gets older and you add more features to it, it gets harder and harder to keep it flexible and add features to it. These issues of arthritis are not so painful with a modeling language such as LINGO. And so an interesting thing you can do is you can model the problem in LINGO, embed the LINGO model in the spreadsheet, and then pass this spreadsheet around. So as far as the end user is concerned, it looks like a pretty straightforward spreadsheet used to store data and store results, but it has this LINGO model hidden in it to do the optimization. So that's what we plan to cover. And let's see if we can do that. So in terms of functions that are supported in What's Best from Excel, here is a list of the functions that are supported. So problem with Excel, if you're trying to work with it, is that it has hundreds of functions, and I don't know what the current count is, several hundred. We support all the popular ones. So in the first line, those functions are pretty straightforward. In a typical optimization system, they frequently do not support the functions listed in red, which are supported and available in What's Best. So, for example, the trigonometric functions in the next line down, the non-smooth functions, max, min, and absolute value in the next line down, the non-smooth, non-continuous functions like int, round, round down, etc. In the next line down. And logical functions, if, ands, you can use them in What's Best. I would recommend use them sparingly because they do make the model combinatorial, but we do recognize them and support them. And finally, some of the standard probability distributions are available in Excel. What's Best also supports the functions of vectors such as sum product, count, SUMIF. We'll talk about SUMIF in particular shortly. Present value, net present value, lookup functions, matrix functions, transpose, index, and match to some extent. So we'll say a little bit about most of those. Now, What's Best adds some functions of its own to help out with some situations that arise when you're doing optimizations frequently. So, for example, if you're solving linear programs, you frequently like to see what the dual prices are. You'd like to have these dual prices placed wherever you'd like in the spreadsheet. You can do that with the WB dual function. So you just plug that in the spreadsheet wherever you want the dual price to appear, and it will appear. We've got some inner product functions that we've added. One curious restriction of Excel is if you want to do a sum product of two vectors, the two vectors have to be in the same orientation. That you can do the sum product of two rows, or you can do the sum product of two columns, but you cannot do the sum product of a row times a column. So we've added the WB inner product that allows you to do that. If you're doing financial portfolio problems, you want to compute the variance of a portfolio and you want to compute algebraically what is called xq x prime or x transpose. So we've got a what's best function WB quad product, which allows you just very easily, without any jumping through hoops, to do that computation. There are various piecewise linear or semi-linear functions that we've added, and we'll talk about SOS2 shortly. Semi-continuous is useful if you say, if you buy anything, you have to buy at least 100 units. That's easy to describe using the WB semi-continuous function in what's best. There's the positive definiteness constraint if you're estimating covariance matrices, which you can add. If you're interested in permutation kinds of problems, there is an AllDiff function, which is popular among constraint programming types, but you can also do it easily in what's best. If, say, for example, you're interested in solving Sudoku puzzles, that's easy to do in what's best. In engineering design, if you're doing heat exchangers, we've added these log mean temperature difference functions there. If you're doing nonlinear networks, the sine power function is added there. If you're doing waiting line kinds of things, the Erlang B and Erlang C functions are available in what's best. And then we've added a number of other probability distributions. So that's what we support. These are the things you can plug into cells when you're working with what's best. Now, in some sense, we support all the functions in Excel, that you can use all the functions in Excel willy-nilly, as long as they are not sort of intrinsically part of the optimization portion of the spreadsheet. So for computing input data and computing output results, you can use any features of Excel that you want, as long as those computations are not sort of active or important in the optimization. And what's best does a good job of figuring that out automatically, so you don't have to worry too much about that. It will give you warnings if you try to use a complex function in Excel that we don't really support in an optimization sense. Okay, so let's do a more specific example. Let's suppose you have a 3-level supply chain, sort of standard, and illustrate how you might do this in Excel, what's best in particular. And it's easy to do because what's best gives good support for the SUMIF function. So how would you represent this in an Excel spreadsheet? I can think of about 3 different ways of doing it. Perhaps the most obvious way would be for this little example. You'd say, okay, I've got 2 plants and 3 DCs, so I'd put in a 2x3 matrix, which would show all possible shipment combinations between plants and DCs. And then I'd have another matrix, maybe on a different tab, which would be a 3x4 matrix, which would show all of the shipping combinations between a DC and a customer. And then I'd have to have some additional stuff in the spreadsheet to hook those 2 matrices together. So that would be one way of doing it. A second matrix way of doing it, which is not quite as obvious, but would be okay, would answer the following situation. So let me throw up a little complication in here. Suppose that you've got one of these customers is a big customer, and you might want to ship direct from a plant to a DC for this customer. That would not quite work with this 2 matrix approach that I just described. So what you could do a second way is just to have one big matrix, which would be a 9x9 matrix, where vertically you would list the 2 plants, the 3 DCs, and the 4 customers, and then also horizontally you would have the 2 plants, the 3 DCs, and the 4 customers, and then you'd have cells in there which would correspond to all of the possible shipment possibilities, in some sense zeroing out the cells that are not valid. So that might be a way of doing it. What might be a problem with this? Well, suppose you have 1,000 or so customers. How big would that matrix be? It would now be 1,000 by 1,000 at least, and so you'd have 1 million cells laying around there, most of them not being important, not usable. So it's a shame to waste good real estate, so you might not like that. So let's look at a third way of doing it. Let's do a quick review of the SUMIF function. The SUMIF function is just like the sum function, except for the red part. So it sums over items in sum over range, the third argument, except that it only sums over those items for which the lookup value matches the item in the lookup range. And where we'll find it useful in our applications in the next couple of slides is we may have a list of arcs from two nodes, and if we're interested in the sum of the flows into a node, we sum over the arc list from two range for those arcs for which the to node is equal to the node that we're currently interested in. So that's the SUMIF function. It's a selective sum, which you might want to have in your toolkit of how to tackle networks in Excel using what's best. And the approach that we're describing here is to use lists and use the SUMIF function. We'll talk about the SUMIF function just a bit more in case you're not familiar with it. So first we would have, say, a tab or an area of the spreadsheet where we'd simply list all of the arcs in the problem. So up at the top, we start with the shipments between plants and warehouses, all of the arcs there. And then in the second half of the list, we have all of the shipments between warehouses and customers, or between DCs and customers. And then we have the data associated with each of them, the cost per unit, the capacity on an arc. Say if you've got a contract with BNSF for so many rail cars per week, there might be a capacity constraint on how much you can ship over an arc. And then our decision, when we get around to describing the full problem, is how much we ship on each arc. That's the blue column in the far right. So the optimization is going to tell us what values to put in there. So that's describing half of the network. The other half is described by the nodes. So here we have the nodes in the network. So the first three are for the plants, the next four for the warehouse, and then finally for the customers at the end. And so here we have the data in the shaded things, the supplies and demands, and we're throwing in an additional wrinkle here of a 0-1 variable of whether we have a distribution center in there or not. So we have this vector in column I, a 0 or 1, depending upon whether we decide to include a particular distribution center in our analysis. And then we'll have constraints in G and column J, which force us to satisfy the various constraints. So now let's look at a little bit of what's going on here in cell F4. So that's the flow into a node. And this is where we use the SUMIF function to calculate the SUMIF, the flow in to node, and the flow in is simply the source that's there for plant A, so that's A, and then but if you look in general up at the very top line, the SUMIF, you can see the way the SUMIF works. It says look in this the arc list for the to destination, and for every destination that matches this particular node, we want to take the sum in the F column, which is the shipment column there. And then the C4 at the end is the supply that's native to that particular thing. So the SUMIF function is useful for calculating the flow in and flow out of a node in the network. And I happen to show the optimal solution here, where the total fixed cost is 19. You can figure out that that's the sum product of the 0-1 vector times the fixed cost, and then the total cost is the cost of the flows plus the fixed cost there at the bottom. Let's do a slightly more interesting looking network. This is a water distribution network, and let's look at how we would do that in What's Best Excel. So here we have 3, 6, 8 nodes. 6 of the 8 nodes are demand nodes. Nodes G and H are supply nodes. So we don't know how much we're going to ship out of G and H, but we do have to ship the amount read into each of the other nodes, A through F. And so the red is the amount that's demanded, and there is some resistance on each arc that's marked in black along each arc. And what we're interested in is what will be the equilibrium flow on each arc and what will be the pressure at each node. So if you're designing a water system, you're interested in sort of how much pressure do we have to have at G and H to get the water through at a given rate. You are interested in what will be the flows in each of these pipes in the network. So let's look at how we would do this in What's Best or Excel. So here again, you would have a node list, and here's what the node list looks like. And so we have the low and high for the pressure in columns C and D. And then in columns E and F, we list effectively the demands. I should say E and I demands. So in node A, for example, it has to have at least one shipped in. And if you look in column I, the most that it can ship in is 1 also. Or if you look at node D in row 7, it needs to have at least 6 shipped in, and at most 6 shipped in. So there are going to be 2 constraints in columns F and H that say you have to, the amount shipped in has to be at least equal to the min and at most equal to the max. And for G and H, the min is negative infinity effectively, and the max, the high, is plus infinity. So we don't know what the shipment in or out is going to be there. This happens to be an equilibrium solution here that I've plugged in, and so the minus values in G and H means that we are shipping out rather than in from nodes G and H. The input data is in the shaded area. The blue are the decision variables, and all of the others are computations of various sorts. Let's look at the arc list. Here is the arc list for this particular network. And so it's a listing of every arc in the problem. And so the shaded area, again, is the input data. The blue numbers are the decision variables, figuring out what the arc flows are. And then the black are the computations that we have to do. And so for relative to each arc, the interesting constraint is that we have to satisfy the flow equation that says that the amount that flows on an arc has to be related to the pressure difference along the arc. And there's a standard formula for representing this relationship between the flow on an arc and the pressure differential between the 2 nodes on the arc, and that's shown on the right there. And it's a fairly general formula that has 2 parameters, sort of a pressure parameter and a friction or fluid resistance parameter there. And qualitatively, though, it says that the pressure differential has to be equal with appropriate coefficients equal to the amount of flow on the arc. So the pressure differential is in row 6 here in the formula, and the resistance is listed in row 8 on the far right there. So we raise the flow to a power and multiply it by the resistance coefficient of that particular link. Now, let's start on the next topic of representing sort of somewhat complex ideas in a spreadsheet, and that's with piecewise linear approximations. And so the general setting is that it's not a mathematical formula that describes a relationship, but rather you describe it with a table of some sort, and you want to do typically interpolation between the table to handle any values in between. So the simplest one to understand is where you have quantity discounts in purchasing. Another slightly more complicated one is in hydroelectric power generation, where the amount of power that you get out of a turbine is a function of both the rate at which the water is flowing through the turbine and also the head or the pressure in the water. So that's hydroelectric. In an energy plant such as a refinery, steam tables are a way of representing sort of this tabular relationship. So let's look at an example. So here is what the price schedule looks like for vendor number 2. And you can see that if you're just buying a piddling amount from vendor 2, he's not giving you quantity discounts at all. But when you start buying more than 13 or about 12 units, in fact, then he starts giving you quantity discounts. And what's best, we'll figure out what is the best amount to buy from each of the 2 vendors total. Example here. And so let's suppose that we have to purchase 18 units of some commodity, and we have 2 vendors from whom we could buy this commodity. And each of these vendors supplies us with a price schedule. This is in the shaded tables here towards the bottom. So vendor 1, for example, says if you want to buy 12 units, that's going to cost you $35. If you want to buy 20 units, it's going to cost you $55. And we're going to use linear interpolation for any values in between. Vendor 2, on the other hand, says if you want to buy 12 units, it costs $36. If you want to buy 19 units, it costs $50. And again, use linear interpolation. And the blue units are our way of describing how we're going to decide how much to buy from each of these. So what we're going to say is that we're going to choose a weighted combination of 2 points on the price schedule. And so for vendor 1, you see the blue 1 in row 17. So that says we're going to buy exactly 5 units from vendor 1. For vendor 2, if you look at the amount to buy, we're going to buy 13 units from vendor 2. And where did we get this cost of 38 from it? Well, 13 units is between 12 and 19, and you get 13 units if you give 0.857 weight to the 1236 line and 0.14286 weight to the 1950 line. So you as a user don't have to worry about that. What's best figures out what the best weights are to use to compute the amount to buy 13, which is a weighted combination of the 12 and 19, and the 38, which is the weighted combination of the 36 and 50. And the only tricky thing is that you have to tell what's best, that the weights that you use have to be adjacent weights. You can't just arbitrarily pick 2 weights from each vendor's column, you have to choose adjacent weights. And so there is a constraint that you can use if called the SOS2, special ordered sets of type 2, and that's listed up at the top. If you look at the very top line, you can see there's this what's best function WBSOS2, and it says, okay, in column H, the range H16 to H20, you can choose any weights you want in there, but they have to be only non-zeros have to be adjacent there. And so that's how you can represent a piecewise linear price schedule. In case you're interested, in this slide we give a little bit of the algebra of this SOS2 idea. So the basic idea is we have this piecewise linear curve here, and associated with each breakpoint is an x value, call it x sub I, and an f function value, call it f of xi. And so we can represent any point on this curve, a point, say, between the breakpoints, by a weighted combination of the points. So there will be three equations essentially describing what we want to happen. So there's an equation for how we compute an x value given the weights w. There's an equation for how we compute the f values given the weights w. And then we have a third equation saying that the weights must sum to 1. And the only tricky part is that if we choose any weights, there we can choose at most 2, and they have to be adjacent weights. So that's what the SOS2 constraint does. It says you can only choose at most 2, and they have to be adjacent. And that allows you to represent any point on this piecewise linear curve. You specify the usage of this SOS2 feature in what's best with this WB SOS2 function specified in some cell. There's a drop-down menu that allows you to specify it. And if you're using the LINGO algebraic modeling language, it has a similar feature called an SOS2 constraint. If you hadn't seen the little example in the previous couple of slides, and you were just doing this in Excel without being aware of what's best, what you might thought of doing would be to use if functions to represent a discount table. So here's an example that came from a user a bit ago. For this particular example, each of 13 suppliers was allowed to have 7 discount levels, and the customer was interested in finding the cheapest way of buying 361 different stock keeping units. And this resulted in an optimization model with 4,646 rows and 7,790 variables. And it was kind of messy. This is what one of the set of if statements looked like for one of the stock keeping units for one of the vendors. And if you look closely at it, you can sort of see what's going on here, that you can see for it's checking, is he in the first interval? No. If not in the first interval, is the quantity purchased in the second interval? And if no, is it the third interval? And the quantity purchased gets multiplied by the appropriate rate in each interval. So that particular model, my recollection is it probably took 20 minutes to solve to global optimality. So what's best can handle if statements like that, but they are very combinatorial, and it can be somewhat slow. After we converted it to a more efficient, this SOS2 style, it was like a minute or so to solve the thing to global optimality. There are some situations where you have a cost or a output that is a function of 2 variables, and these two, this functional relationship is again described by a table rather than some explicit mathematical function. And the question is, can we do that in what's best? And the answer is yes, and we'll talk about 2 examples. One is modeling the output from a hydropower unit. And so this is described graphically here. The 2 inputs are, one, the volume of water that you're allowing to flow through the turbine on a particular hour, The other input is the head, the pressure that is available at that particular hour. So the level of the reservoir may rise or fall from hour to hour, and so the amount of power output that you can get depends upon both the level of the reservoir and the output rate at which you're putting stuff through. So the power output is a function of those two inputs, the head and the volume of water released. And the question is, can you represent that by this SOS2 tabular style of input? And the answer is yes. A second example where you have a relationship which is a function of two variables is in energy plants of a different sort. For example, oil refineries perhaps, and that is where steam is used to do various actions. So steam is a very useful thing. It's used all over the place. It's used in paper plants. It's used to heat buildings. It's used to provide motive power, so forth. You have to know you have to model the behavior of steam if you want to use it efficiently. And so there are these things called steam tables, which are very common if you're in a refinery, say. And the way to think about it is you have two inputs, pressure and temperature, controlling some volume, and then one of the outputs is the volume that is occupied by a unit of steam based on the pressure and temperature. And you can see as the temperature increases in the left there that the volume increases. Also, you can see as the pressure increases, the volume decreases, which makes sense. Now, a second output that you're very concerned about in an energy plant is something called enthalpy, which is essentially the stored energy in the system. And not surprisingly, you can see that the stored energy measured in BTUs per pound or in calories per gram or whatever units you wish to use, SI or English units. You can see that as the pressure increases, the stored energy increases also for a given number of moles of steam that you're storing. Enthalpy as a function of pressure is not quite as intuitive. You can see, in fact, that the enthalpy actually goes down if you're holding the temperature constant and the pressure is increasing. This is not quite as intuitive, but that's what's going on. So it turns out you can, in fact, represent such tabular relationships also. You essentially just use this SOS2 device twice, so to speak. And that's done down in the bottom right, where you see the blue variables, where each blue variable is the weight that is applied to a given combination of pressure and temperature, and that's how you determine the output. So for example, that if we're going to have a pressure of 97.52 and a temperature of 478.76 over there on the middle left, you can see that you can achieve that by putting these weights on the lower right in the blue here on the related points. It's sort of midway between 90 and 100 pounds per square inch of pressure, and it's midway between 450 and 500 degrees Fahrenheit of temperature. And you simply use the SOS2 device twice and to say that the points have to be adjacent. The marginals have to satisfy this SOS2 feature on the pressure dimension, and also they have to satisfy this two adjacent points, non-zero, on the temperature dimension here. So I won't go over the nitty-gritty details here, but these spreadsheets are available sort of publicly on the LINDO website in the library. If you go to the models library and you just do a word search on things like steam tables, you'll find models there, and it's simply a matter of sort of plugging in your own situation. If you're interested in the algebra behind all this, here's the algebra, and we won't talk about it here, but it is there. And so if you're concerned about exactly how do you set up the sheet, this gives you some of the details. Next topic. So let's look at the situation now where we do have explicit mathematical expressions for a particular relationship. And in this case, they're quadratic. And we'll do two situations. One for financial portfolios, and the other will be for nonlinear blending. Very standard application of quadratic expressions is for computing the variance of a portfolio, a so-called Markowitz portfolio. And here is a standard statement of it for a portfolio where we're considering 7 different investments, 6 Vanguard funds plus CDs. And the input data is in the shaded area again. The estimated future returns for each investment, the standard deviation for each investment, and then a matrix below the correlation matrix. And so we need to compute the variance of a portfolio consisting of a weighted average of these investments. And so the optimal solution for this particular one, if we look in row 13, happens to put nothing in CDs, but a fair amount in Vanguard 40 fund, a rather bit more in the Vanguard 058 fund, and then modest amounts in the other funds. And we have the standard constraints that the weights have to sum to 1, and we would like to have an expected return of at least 5.5% up there on the right in row 9 of the spreadsheet. That's our target return. So this is a standard Markowitz portfolio. And the tricky part is to compute the variance of the portfolio. And this is essentially done by a single computation in what's best. There's a function called quad product, and you simply have to say, essentially, here's the correlation matrix, and here's the vector I want you to multiply this by this correlation matrix. So if you're comfortable with matrix notation, you want to compute something called xqx prime, or a little bit further down towards the bottom in row 26, you want to compute the weight vector x times the standard deviation vector times the Q matrix times the transpose of the standard deviation vector times the weight vector, and that will give you the variance of the portfolio there in the blue in column L, row 25 of the spreadsheet. And you do it with just a single function in what's best called quad product. And you simply say, here's the covariance matrix or the correlation matrix, and here's the vector I want you to multiply it, pre-multiply it, and post-multiply it by to give me the variance of the portfolio. So it's very easy to set up a Markowitz-style portfolio model in Excel what's best. Of our second example of using a quadratic function in a model, we'll look at a very simple, oversimplified perhaps, blending model. And so it turns out when you blend certain ingredients to produce gasoline, they do not blend linearly. So let's look at a situation here where we have half a dozen different materials that we might blend into gasoline. So if you look at alky and HCAT together in row 9, they have fairly good octane ratings, motor octane, certainly for alky alkylate, 105.4. But if you look in the quadratic matrix below, there's a -17. And what this means is that if you do a mixture of HCAT and alkylate together, there's sort of like a penalty of 17 units that you lose in terms of octane rating. So if they blended just linearly, row 9 by itself would tell you what the octane would be. But there's this interaction between ingredients which causes the octane to be hurt. And it's interesting, if you look at butane, the column G, the rightmost column, its interaction term is 0 with everything else. So butane blends linearly with everything else according to this data that we have here. So what we'd like to do is we'd like to figure out how to do a blend so that we achieve a certain octane level, certain motor octane level, essentially of 90. And that's listed up at the top left in row 3. So again, the shaded area is the input data. So we'd like to achieve an octane rating of 90, and we can sell the stuff for 140 per unit. And the question is, how should we blend the stuff, our ingredients, so we achieve this octane rating of 90. We have to pay for the ingredients that we buy in row 7, and we want to maximize our profit while achieving this octane rating and taking into account that things blend nonlinearly. And in terms of representing this nonlinear effect, that's fairly easy to do in what's best. Down in row 24, the leftmost cell, we compute the achieved motor octane rating, and all we have to do is write this WB quad product that says that take into account 3 terms: the variable vector, which is really row 17, how much we blend of each item, and the linear term, which is the MON alone, the linear effect, and then the quad effect is this interaction matrix here. And it says what we should do is we should use 70 units of the alkylate, 80 units of the butane, not use any of the heavy cat-cracked material, and which is not surprising since it interacts very negatively, certainly with the alkylate, and also somewhat negatively with reformate. So again, it's quite simple to take into account this quadratic interaction using the WB quad product function in what's best. Let's continue talking about covariance matrices, and let's take sort of an earlier view, and let's suppose that we have to estimate or come up with a covariance matrix. So perhaps for the Markowitz financial portfolio problem, you want to construct a correlation matrix, let's say, and you don't have really good data for it. And so one way you might do it is you might just ask people, what do you think is the correlation between IBM and Apple? And in various ways you collect estimates of what the correlations are between various stocks. And then the question is this a valid correlation matrix? Well, what does it mean, mean for a correlation matrix to be valid? It should be so-called positive definite. What happens if it's not positive definite? Well, it may be then that if you try to compute the variance of a portfolio where you use an invalid correlation matrix, you'll come up with an estimate that gives you a negative variance, which does not make any sense. So that's the problem we'd like to tackle. How can you make sure that the correlation matrix or the covariance matrix that you estimated is in fact valid, that it is positive semi-definite, that it is convex? Let's work with a specific example, and again in the shaded area up towards the top we have an estimated covariance matrix between IBM, GE, Apple, and XOM. And can anyone detect that this is not a valid covariance matrix? In fact, it is not a valid one, and I won't say why, but you might be able to test it. And so what we would like to do is we'd like to come up with a covariance matrix which is valid and is as close as possible to our original one. So down at the bottom, we're going to come up with an estimate of the differences between these two matrices, and that we're going to come up with a matrix down in the middle here that is in fact a valid covariance matrix. And so what we're going to do is, we'll say, come up with a new matrix for which the sum of squared differences between all of the original values and my new matrix are as small as possible, subject to the constraint that the new matrix is positive definite. So that if I try to compute portfolio variances with it, they'd come out right. Or if you try to solve an optimization problem with this covariance matrix, you won't get a message saying, we cannot solve this problem for you because the matrix is not positive definite. So here's the situation. Here's the original value, the original matrix that is our estimate. And here is our adjusted matrix right here. And here is the matrix of differences between the two matrices. So we want to make this bottom matrix as small as possible, looking at the squared amounts of each element. So square each element, sum them up, and that's what we want to minimize. So down at the bottom, our objective is to minimize the sum of squared differences. And then the only constraint is that this middle matrix here has to be a valid covariance matrix. And in what's best, we have a nice little constraint that says this matrix is constrained to be positive definite. So it's WB pos D. And all you have to do is up at the top here in J14, we have this constraint that says this range from D14 to G17 has to be positive definite. And we simply click on solve, and it will give us this solution right here, saying here's this new matrix, which is in fact positive definite. The next topic we want to talk about is another engineering design optimization kind of problem, and that is the modeling of heat exchangers. So heat exchangers are very common, especially in oil refineries, but they're also in your car radiator is a heat exchanger, your air conditioning coils are heat exchangers, so they're all over the place. And What's Best has one special function that's helps simplify the modeling of heat exchangers. It's something called the log mean temperature difference function. So there's a special function that you can use in Excel, What's Best, WBLMTD. And so let's talk a little bit about that in terms of giving an example. So here's an example of a heat exchanger. The most common form is the so-called shell and tube design. And the basic situation is you have two fluids, a hot fluid and a cold fluid. And the purpose is to cool the hot fluid and warm up the cold fluid. And the internals look something like that. And the kinds of questions we'll be concerned about are as follows. So what should be the size of the heat exchanger? We'll give ourselves a continuous variable here, the area of the heat exchanger. Obviously, the more heat you want transferred, the more area you want, the bigger the heat exchanger you want. In practice, you may have a discrete choice of heat exchangers that you could use. You may have a decision variable of the flow rate of the hot stream or the cold stream. Frequently, it's the flow rate of the cold stream that if you're along Lake Michigan or along some lake, you're pulling in some lake water and you're using it to cool down some other fluid. And so you may have a decision variable of how much lake fluid do you take. Another decision variable might be the outlet temperature of the cold fluid. If you're returning the water to the lake, there may be constraints or costs to returning water that's a little bit on the hot side. So that may be a decision variable. So these are roughly the decision variables that may or may not appear in a particular problem. Size of the heat exchanger, the flow rate for either of the streams, either or both of the streams, the inlet temperature, the outlet temperature, more typically the outlet temperature. And then, of course, you're concerned about the amount of heat transferred between the two streams, measured in either calories if you're using SI units or BTUs if you're using British units. So let's look at a slightly more specific example and see if we can understand it. So here is a what's best spreadsheet set up for solving a very simple heat exchanger optimization problem where the main decision variable is simply the area of the heat exchanger. And as with most of the spreadsheet examples here, I give the name of the spreadsheet up in the upper right here. So this one is called Heat Exchange WBLMTD Fun 2. So if you're looking on the thumb drive or if you're searching our models library, that is what you would be searching for. So here, again, following the convention of our previous examples, the yellow shading indicates an input parameter, which is a given, and the blue font indicates a decision variable. So we're given the hot temperature, 185 degrees, which is an input data, and the cold input temperature, which is 50 degrees, or bringing in sort of standard lake water. And we want to cool the hot fluid down to 140 degrees. So that's in row 19. You see the 140. And a decision variable is the outlet temperature of the cold fluid. And we have a constraint that it has to be less than 95 degrees Fahrenheit. And then some computed values are the difference in temperatures at the hot end, where the hot stream comes in and the cold stream departs, and the temperature difference at the cold end, where the hot stream that is cooled down departs and the cold water enters. And so the amount of heat that is transferred between the two fluids is related to this temperature difference between there, and that's the crucial thing. And so to sort of summarize things in a nutshell, the key thing of importance is the average temperature difference between these two fluids over the entire length of their flow through there. And if we know the average temperature difference, then we can calculate the amount of heat that is transferred, and we compute the various temperatures involved and so forth. So here is where this additional function from what's best comes into play. So if you look in cell B29 up at the top, in the very top line, you can see we're using WBLMTD, the log mean temperature difference. And so the average temperature is well approximated by this log mean temperature difference. And it's based on the temperature difference at the hot end and the temperature difference at the cold end. So once you have that, you can write a complete model for optimizing heat exchanger system. So here, this example optimizes just the design of one heat exchanger. In a more realistic problem, there may be a network of heat exchangers that you're interested in modeling. And if we look a little bit closer at this one, I won't go through all the details of the model, but you can see the objective function is based on the cost of the area. Sort of the bigger the area, the bigger heater exchanger you use, you're going to have to pay more for it. And then we're also going to give ourselves a cost based on the amount of the cold stream that we use. So if we're pulling in lake water, we may have to pay a price for how much lake water we use. So we're minimizing the combination of the heat exchanger cost and the cost that we have to pay for the cooling water. In other situations, there may be constraints on these things, discrete choices, so forth. So that's the objective function. And then we have various flow balance constraints, which you can see are summarized here. There's one related to the heat transferred per unit time based on the conductivity and the mean temperature differences. That's where we use this special function. And we can certainly measure the heat loss per unit time of the hot fluid. That is based on the temperature difference between when it comes in and when it departs. And we know the specific heat of the hot fluid. We can compute how much heat was given up by the hot fluid. We do the same thing for the cold fluid. We look at the temperature difference between when it entered and when it departed. And we know the specific heat of the cold fluid, and we know how much is flowing through it. We can calculate the heat lost. Those two things have to be equal. So you've got these various flow balance ones. So that's how you can model a heat exchanger quite easily in a spreadsheet with what's best using this log mean temperature difference function that is available there. Our next major topic for the talk this afternoon is modeling uncertainty. So there are a number of different names that are applied to it. Scenario planning is one, stochastic programming is another one. So we'll frequently just use SP to denote when we're talking about modeling of uncertainty, scenario planning or stochastic programming. The applications of it are quite extensive in financial planning, capacity production planning, fuel purchasing, exploration for a petroleum company, metal blending, where the composition of the scrap that is an important input is uncertain. In fleet assignment problems for airlines, there's all kinds of uncertainty, like will there be a big problem with a certain type of aircraft, which will cause you trouble. Demand for electricity is uncertain. So a lot of different examples of uncertainty. And so we're going to talk about how it's easy to model them in what's best. This next little example is motivated by a study we did many years ago for General Motors. And the question was which plants should be closed and which plants should we keep open, or which plants should we perhaps open? What kinds of plants should we perhaps open in the face of uncertain future demand? So in this particular situation here, we have 3 different possible plants that we're considering: Atlanta, Cincinnati, and St. Louis. And associated with each plant is a fixed cost per year of having it there. And each one has a capacity. So for an existing plant, it's pretty clear where the capacity might come from. And our decision is which of those plants, any 1, 2, or 3 of them, should we have open in the face of uncertain demand. And let's say a little bit about demand. So a little bit further down in this spreadsheet, if you look in rows 17, 18, and 19, we have demand, which is represented by 3 possible scenarios of what could happen. So scenario 1 has fairly small demand at Chicago, a rather large demand at Miami, and it has a probability of 0.3 of occurring. Scenario 2 has 33 units of demand at Chicago, 11 at San Antonio, and only 1 at Miami. So it's dramatically different in terms of what we expect to happen in Miami and Chicago. And scenario 3 is sort of an optimistic scenario in terms that the demand is quite high at Chicago and demand is fairly high at Miami also, although the demands are a little bit lower at San Antonio and New York. So up in the upper left, let's review what is going on here and sort of how we have to think about this. So in stage 0, we have to decide which plants to be open without knowing which demand scenario is going to occur. Then in stage 1 at the beginning, the demand occurs, and then stage 1 at the end, we decide how can we satisfy the demand in the cheapest way possible, given, or the most profitable way possible, given the capacity that we have installed at this point. So let's look at the spreadsheet a little bit more again. So we've got some fixed costs and capacities, and then we have some decision variables, which are 0 or 1. And so in column D up at the top, we've plugged in a decision of 1. So this corresponds to the situation where we have the plant in Atlanta open, but the plants in Cincinnati and St. Louis are not open. They're closed. And the row 13 is going to be a placeholder for whatever scenario happens to occur. And then the actual list of possible scenarios are down in rows 17, 18, and 19. And a little bit further down, we specify what the revenues are per unit shipped. So these revenues per unit shipped, 5, for example, for shipping from Atlanta to Chicago, corresponds to, what's the selling price minus the variable costs. That's where those revenues come from, loosely speaking. So if we knew which plants were in place and their capacities, and we knew what the demands were, then we would have a so-called transportation problem. Simply, given here are sources of supply, and here are demands and what demands are needed, and the capacities at each place of the supply places, what's the cheapest way of satisfying that demand? So that's the situation. Now let's see if we can understand this a little bit better. So if you plug in scenario 1 and you solve the corresponding transportation problem, or solve the decision problem, I should say, it says it's the best thing to do is open Atlanta. That's the most profitable thing to do. If, on the other hand, scenario 2 holds, then the best thing to do is open St. Louis and satisfy demand there. And not surprisingly, if scenario 3 occurs, that's the high demand scenario, then it says we should have both Atlanta and St. Louis opened there. So at this point, we say, well, what would you do? Which plant should you open? We've looked at the 3 scenarios. What's the best thing to do? So the way we want to solve this is we want to, at stage 0, decide which plants to open, which one or more plants to open, so as to maximize the expected profit. Regardless of which scenario occurs, if we average over all possible scenarios, what is the best decision to make at the outset in terms of opening plants, given the probabilities in column F and the possible scenarios in rows 17, 18, and 19. So if you made your decision, let's see which one of those possibilities we open. Well, if you look in row 8, it appears that the best plant to open is Cincinnati, not St. Louis or Atlanta. So Cincinnati is not best for any scenario, but it's the best one in a hedging sense, that it doesn't do poorly in any of the 3 scenarios. And to understand this, you can probably look at the revenue per unit shipped table down in rows 22 to 24, that the St. Louis plant is really great for satisfying Chicago demand when Chicago demand is high, but the St. Louis plant is not very good for satisfying the Miami demand. So in the scenarios where Miami is high, St. Louis is not very good, whereas Cincinnati is good in between. So using stochastic optimization or scenario planning is good at identifying which are the best hedging sort of decisions, if you wish. There are various report options available when using the stochastic option in what's best. Perhaps the easiest to understand is the histogram. Here is the histogram for our little plant location problem. It only has 3 bars in it because there were only 3 scenarios in it. In general, you can have as many bars as you have scenarios, but typically you probably if you have 1,000 scenarios, you generally don't want to have more than about 20 bars in your histogram. The histogram in What's Best is much easier to call up than it is to generate a histogram in Excel. Another thing you might want to do after solving an optimization problem in What's Best is to look at individual scenarios. So there is a scenario dialog box that you can call up to bring up specific scenarios and display them in the spreadsheet. And each scenario corresponds to a different set of values in a spreadsheet, so you need to call up each individual one to look at a specific one. It is not difficult to add the stochastic feature to a spreadsheet. You simply first construct a deterministic version, and you may want to debug the deterministic version first. And then What's Best has dialog boxes for adding the stochastic feature. So the major things that you have to do is use that dialog box to identify the random variables and also the decision variables that are in the various stages. And then you have to specify a distribution for each random variable. And then finally some sort of bookkeeping information, the sample size you want to use when you do sort of the sampling from the distributions, and then any additional reporting such as histograms that you might wish to report. And so we've shown a dialog box here, a typical dialog box here, where we're specifying that the cells in B13 and E13 have a discrete distribution, and that the discrete values are stored in the range B17 to B19, and then that gets stored in the spreadsheet. So it's relatively straightforward to insert the stochastic information into a spreadsheet. Our next problem is a multi-stage decision making under uncertainty problem. We would like to save and invest some money in order to put our child through college in 3 years from now or 3 periods from now. So we feel that we would need $80,000 in order to be properly prepared. So up there in row 3 of the spreadsheet, we've got the 80 for the goal for wealth at the beginning of period 4, 3 periods from now. And down in row 9, we indicate our beginning wealth. Our beginning wealth is $55,000. So we've got $55,000. We'd like to grow it to $80,000 in 3 periods. And things are uncertain, so we'd like to decide how to allocate our investment appropriately in order to achieve that. Well, how can we help achieve that goal? Off on the far right, we give ourselves 2 investment possibilities, stocks and bonds. And to represent uncertainty, we use only 2 scenarios, A and B. Scenario A is kind of an optimistic scenario in which we guess that stocks will grow by a factor of 1.25, bonds will grow by a factor of 1.14. If scenario B occurs, things are much worse. For stocks, they only grow by 1.06, and bonds by 1.12. Now, how will we measure our success after 3 years? Well, we give ourselves a little downside risk utility function. So if you look in rows 4 and 5 up ahead, we say that if we fall short of the 80,000, we're going to penalize our goodness measure by a factor of 4, whereas if we achieve the 80,000 or anything higher, we give a weight to 1 of that. So it's an interesting piecewise linear utility function saying that it grows at rate 4 until we hit 80,000, and then it grows at rate 1. So that's how we'll specify effectively this target. We'd certainly like to achieve the target of 8, and if we can go over it, that would be good too. And if we don't achieve it, we'd certainly like to get closer to it rather than farther away from doing. So if you look down at row 18, we have this thing called net utility, and if you look at the expression for up at the very top row, we're essentially taking 4 times the amount by which we fall short, subtracted from 1 times the total wealth that we gain. So that's the problem. How much should we allocate to stocks and bonds each period? So what we do in the second and third period is probably going to depend on how things turned out in the first and second periods. So let's look at what the results are. So in the next slide, we will show what we should do if any of the 8 scenarios occur. Where do the 8 scenarios occur from? Well, there are 2 possibilities each period. There are 3 periods, so it's 2 times 2 is 4, times 2 is 8 possible scenarios of what can happen. So let's look at what happens depending upon which scenario occurs. So when you run what's best with the SP, stochastic programming scenario planning option, the default option is that you can get a listing of all of the scenarios that occurred. So for this particular one, there are 8 scenarios. They're listed vertically down on the left there. And then across horizontally, we've listed the various performance measures of interest. And you can specify which performance measures you want listed when you set up the model. And so here, for example, we can see that in stage 0, we decide that the optimal thing to do is to put 41.47 into stocks and put 13.52 into bonds. That's how we allocate the 55,000 that we start with. And notice that that allocation is the same regardless of the scenario, that it has to be that way. Then 2 possibilities occur there, and you can see in stage 1, the second period, the allocation depends upon which scenario occurred. So we'll put either 59, we'll have a wealth of 59 or either 67, depending on which scenario occurred. And we'll invest either 36.74 in stocks or 65.09 in stocks, depending upon which scenario occurred. Now let's look in particular at the highlighted section there, which is we look at how much wealth we had in period 2, and then look at how we allocate our investment in either stocks or bonds. So notice that if we had 71,000 starting wealth in that period, we'd put 0 into stocks and put all of it into bonds. If we had only a wealth of 64, then we'd put the entire 64 into stocks and nothing into bonds. Similarly, if we had 83,000.84, we'd put all of it into stocks. So this is kind of curious. Notice this, that if we had very low wealth, 64, we put everything into stocks, or if we have a fairly high wealth, or quite high wealth, 83.83, we put everything into stocks. If we have an intermediate wealth, 71.42, see down in scenarios 1 and 2 or scenarios 7 and 8, in those cases, we put everything into bonds. Now, why is that? If we have an intermediate wealth, we put everything into bonds, but if it's an extreme wealth, either really low or everything high, we put everything in stocks. Well, it's because of that utility function. So if we have 64, a wealth of 64, it turns out, if you check things out, there's no way that we can make the 80,000. So we might as well come as close as possible to the 80,000. And which of the 2 investments gives you the highest expected return? It's stocks. So you put everything in stocks to get us close to 80,000. We know we're not going to make the 80,000. We might as well get as close as possible. On the other hand, if you have 83,000 in hand already, you've already made your goal. Then you might as well get as much more additional as possible. What's the best way to get expected amount as possible? Put everything into stocks again, because they have the highest expected return. So it's sort of interesting to look at how the utility function, your utility function, this downside risk kind of utility function, affects how you do allocation here. For reference, here's the histogram for the college planning problem. There are 5 possible outcomes, and you can see that there's about a 0.13 probability that we don't make the 80,000 target. We'll quickly go through a couple of other examples of multi-stage planning with what's best. Here, for example, is a yield management or revenue management kind of problem. Situation where we've got 20 seats that we want to sell over the next 4 periods, and we're going to use a policy of raising the price as we get closer to the end date, sort of when this plane is going to fly. And the question is, how many seats should we hold back in each period? So if you expect that you're going to have a substantial demand right before you have to use the seat, you may want to hold back some of the seats. So that's fairly easy to formulate in what's best, also as shown in this sheet. Here's another example of modeling a put option in what's best. So if you have a put option, this is the right to sell a specified stock at any time you wish until the expiration of the option. And you see the price each period, and you sort of have to decide, is this a good time to sell or not? So you can figure out the optimal policy with this little model here. Here's the histogram for the profit, expected present value for this little option that has an expected value of $3.84. But notice the rather odd-looking distribution for it. Most of the time, like 60% of the time, you don't make any money at all, and it's just occasionally, like about 10 or 11 or 12% that you make $13 from it. So you make your expected profit only from the sort of 1 in 10 situations where you make a lot of money. So it's frequently good to see the histogram for a decision-making under uncertainty problem so that you know what sort of risk you're facing. A word about sampling in what's best. It by default uses Latin hypercube sampling, which essentially means you divide the possible outcomes into bins, where the probability of drawing from a bin is related to the probability that the random variable should be in that bin. And it tends to give much better sampling. So look at the leftmost histogram. That's the histogram you get if you use Latin hypercube sampling. The upper right bin is if you just use ordinary random sampling. So this is from a normal distribution with mean 100 and a standard deviation 10, and you can see the distribution on the left looks much like it's getting close to the true distribution much more quickly than just using plain random sampling. You have a choice of different sampling methods. So another one is antithetic, and that's listed over in the right, and it looks like Latin hypercube sampling with antithetic simultaneously isn't quite as, doesn't converge quite as nicely as just plain Latin hypercube sampling. You can request what's best stochastic to provide you with something called the expected value of perfect information. And the idea behind it is on this line down towards the bottom. So perfect information would correspond to, say, if you you were selling some product, say ice cream or something, that depended heavily upon what the weather is like. And so if you can imagine, if you had perfect weather forecasts, you could make your stocking decisions much more wisely. And so perfect information corresponds to that, and the expected value of perfect information is how much more money you could make if you had perfect forecasts. So now another piece of information that what's best gives you is the expected value of modeling uncertainty. This is at the extreme left, where you disregard uncertainty,
and you just use the mean values of random variables. So you act as if the random variables are really deterministic, and so if the mean demand is 50, you just act as if the mean demand is 50, and you'll probably stock 50 exactly. And that may not be a good thing to do if demand varies between 40 and 200. And so EVMU, expected value modeling uncertainty, is how much more money you make by taking into account the probability distribution as opposed to just using expected values and acting as if all your forecasts were perfect when in fact they are not. Here we have a little example of the calculation of expected value of perfect information and the expected value of modeling uncertainty. So this is for a little newsboy or news vendor problem. And so the expected value maximum profit from the optimization is 2109. If you did wait and see, which corresponds to having perfect forecasts, your profit would go way up to 27.99. So the expected value of perfect information is the difference between those two. On the other hand, if you assume that all random variables always took on their mean value and then made your decision cardinally, but then judged it when in fact the random variables or the demands are random, the cost of that policy or the profit of that policy would be 2081. So in this case, the value of modeling uncertainty is about 28, the difference between those two. A nice thing that you can do when using stochastic optimization with what's best is that you can, in effect, enforce a utility function on the results. And so a standard one is a downside risk one, where you say, well, there's a certain threshold where if my profit is lower than that, that's kind of embarrassing. And I have to report that to my stockholders or to my wife or something like that. And so I worry about if my profit is below the threshold. So I'm going to compute a penalty value, which is the amount by which I fall short of my target. And I'll perhaps put a constraint on that or put a weight on it in the objective function. So here I'm suggesting that we put a weight on it so that we look at how much we fell short in every scenario, weighted by the probability of that scenario. That's the expected downside, and say that has to be less than or equal to some tolerance. So both the threshold and the tolerance are parameters that you would input depending upon your taste for risk. And so let's look in a moment at how that might affect things in an actual optimization. A number of years ago, we did an optimization study for General Motors, stochastic optimization, concerned with what kinds of plants they should have open. Things like, should they have flexible plants? How many flexible plants? Which old plants should they close? Questions like that. And we did two sorts of analysis for this particular graph. One where we simply maximized expected profit with no constraints on downside risk. And that corresponds to this red histogram there. And then we put in a constraint on downside risk. And it's effectively a knob, and you can crank up how tight you want that constraint. So we put a modest constraint on downside risk, saying we don't like situations where we lose a lot of money or don't make very much money. And so the histogram, when we did that, is the green one that we got there. And I suspect that most people would prefer the green histogram. If you're a gambler and really like risk, you might like the red histogram nevertheless, because it might give you, that 284 on the right, whereas the green histogram at best gives you about 190 there. But I suspect most people, most managers who have to sort of listen to the voice of their stockholders would prefer the green histogram. And of course, the question is, what do you give up in order to get the green histogram rather than red histogram? you give up a certain amount of expected profit by doing that.
We have been talking about ways of trying to take into account uncertainty in a systematic way. Let's talk about another idea that can sometimes help when there's some uncertainty of some sort in your problem. And this approach is that what's best has a capability when solving an integer program of giving you the k best solutions to that integer program. So you can specify k, like half a dozen, or something like that, and what's best will give you the half a dozen best solutions to the problem. So for example, if there are 5 alternate optima to your particular problem, and you ask for the 6 best solutions, you'll get the 5 alternate optima plus the next best solution after that. In order to illustrate this approach, let's look at one of the simpler integer programs around, a knapsack problem. So you're going off on a picnic and you have to pack a knapsack, and you've got a little over a half a dozen different items that you might pack in your knapsack. So what we've done here in the shaded area, the input data for the various items that we might put in the backpack, we've given their characteristics. So for example, brats have a weight of 3, and beer has a weight of 3. Brats only has a value of 1, beer has a weight of 3. On the other hand, for example, if you want to put in a watermelon, that has a weight of 7 and a value of 9. And if you solve this problem and just ask for the optimal solution, here is the solution that we got back. It says, okay, put in a frisbee, salad, and a watermelon, and you'll get a value of 25. So there is no way of getting more than a value of 25 from a knapsack that has a capacity of 15 pounds. That's what our unit of weight is. Now, you might say, gee, I was kind of hoping that beer maybe might got included in the solution. So you ask for the half a dozen or so best solutions, and let's see what we get. There are several different ways in which you can look at the k-best solutions. One way is just in a tabular form where they're listed out. And so here we've listed out the 7 best solutions to our little knapsack problem. And whoa, look at this. There's an alternate optimal of 25 here for the second solution, and it does include beer in the solution. So that sounds like it might be good. It's also interesting that maybe if you're willing to give up 1 unit of value, if you go to solution 3, that has an optimal value of 24. It also includes beer in the solution, and it also includes the item that was dropped, which is the watermelon. So in case someone else in your party really cared about watermelon and you really cared about beer, you can get both of them with that third solution only giving up 1 point. If the other person is sort of indifferent what's in the knapsack, the second solution might be just fine for you. So that's k-best solutions. Quite easy to request, very useful, and it's been our experience for typically for integer programs, they have alternate optimal solutions, so it's good to find them out. What we'd like to talk about in this section is embedding a model that's been written in the LINGO algebraic modeling language inside of a spreadsheet. Now, why might you want to do that? Well, those of you who have worked with spreadsheets, you may be familiar with the term arthritis that is sometimes applied to spreadsheets. That is, as a spreadsheet gets older, a lot of people work on it, or one person perhaps works on it and adds on lots of different features and complications. the spreadsheet becomes arthritic. It becomes very difficult to move on to additional features when the spreadsheet gets fairly complicated. Algebraic modeling languages, on the other hand, are rather more flexible. So spreadsheets are good if you have two-dimensional problems like suppliers and customers or products and time periods. However, if you have more than two dimensions like suppliers and customers and time periods and products, it gets kind of messy in a spreadsheet. It can get kind of messy in a spreadsheet. Algebraic modeling languages, on the other hand, don't care very much whether you have 1 subscripts, 2, 3, or 4, or 5 subscripts on your variables. So you may be interested in using an algebraic modeling language when you have a complex, messy problem. The kinds of complex, messy problems that we've encountered that satisfy this condition are things like cutting stock problems or routing problems. It's not too difficult to write models in LINGO algebraic modeling language for handling cutting stock problems or routing problems, but it is very difficult to try to write a procedure for solving a cutting stock or a routing problem in Excel by itself. So let's illustrate ideas here with a staffing problem, which is sort of at the borderline. It's not too difficult to do in a spreadsheet, and it's not difficult to do in the LINGO modeling language, but we'll use it as an example. So here we have to satisfy some staffing needs for 7 days of the week in a cyclic fashion, like the week wraps around. And so each person that we hire on a given day works for 5 consecutive days and then is off for 2 days. And what we've done here is we said, okay, let's just take a simple approach and have a constant number starting each day of the week. So in the required row, we need 19 people on Monday, and then things drop off a little bit, pick up a little bit on Thursday, and even more on Friday, and then drop off to 12 on Sunday. And so if we hire just the same number of people each day of the week, you would need to hire 4 people on each day of the week, and that would give you 20 people on duty every day, and that would satisfy the need for every day of the week, and the total persons hired would be 4 times 7 is 28 person weeks that you would hire. Can we do better than that? So we've got a LINGO model embedded in this particular spreadsheet, and we can access it by pressing on the Solve button. And let's see if we can improve this 28 by optimizing a bit by pressing the Solve button. So here it appears we can do quite a bit better. So instead of having 28 person weeks, we only need 22 person weeks, and we do a pretty good job of matching the on-duty requirements with the actual number of people by starting 7 people on Monday, 3 people on Tuesday. Don't start anyone on that low demand day or Wednesday. And don't start anyone on Sunday, which is also a low demand day. And the graph indicates that we have in fact done a perfect job of matching the staffing needs with the numbers supplied. Now, in general, for a staffing problem, you can't be guaranteed to get a perfect match like that, but in our little example, we were able to achieve this. And we did this with a staffing model that was written in LINGO embedded in the spreadsheet. Now, doing that embedding is fairly easy to do. Let's look at that. So here's an example of a supply chain kind of model done with data in a spreadsheet, but using a LINGO algebraic model embedded in the spreadsheet. So here is the node data for our little supply chain problem, where the 2 plants have supplies of 9 and 8. The warehouses or distribution centers don't have any supplier demand. And then we've got 4 customers with demands of 3, 5, 4, and 2. and we have to worry about how to supply those customers. The other type of input data we have for this problem is the ARC data, and this shows in list form all of the possible shipments. So there's a possible shipment from plant 1 to warehouse 1. It has a cost of 1, and you can ship up to 4 units over that ARC. From plant 2 to warehouse 1, cost is 3. There's no limit on how many you can ship there. And the objective is to find the lowest cost shipment combinations from plants to warehouses to customers, satisfying the capacity constraints and satisfy the demand constraints. So if we click on the Solve button, we should see what the shipments are for those decision variables of how much to ship. So after clicking on the Solve button, we see that the decision variables of how much to ship have been plugged into the how much to ship column. So for example, we'll ship 6 units from plant 1 to warehouse 1, and then warehouse 1 will ship 3 of those units to customer 1, and warehouse 1 will ship the other 3 units to customer 2. So that's solution, and the total cost of that solution is 100. That's the least cost solution for satisfying those demands from the supply we have available at our plants, not exceeding the capacities of any of the ARCs. And this is what the embedded model looks like. It's a standard LINGO model, and it's simply stored on a tab of the spreadsheet, and it has some statements in it around lines 11, 12, 13, and to 15 to retrieve data, input data from the current spreadsheet, and then in line 17 it sends the solution data, the flow data, back to the spreadsheet. So a couple of nice features to this approach, that as far as the user is concerned, it just looks like a spreadsheet model. They can pass the spreadsheet around, and the LINGO model goes with it. It can be useful for complicated problems, in that LINGO models tend to be easier to maintain than spreadsheet models. So for example, if you want to increase the number of plants, or increase the number of warehouses or customers, all you have to do is change the data in the spreadsheet. You don't have to do anything to the equations that describe the model. So the equations that describe the model are in rows 20 through 33 of this little tab on the spreadsheet. And those statements do not have anything to do with the size of the particular data you happen to be solving in this run. Those statements effectively adjust automatically to the size of the current problem. There's no issue of copying equations or anything, or formulas in the spreadsheet when you change the size of the problem. There's a lot less arthritis in this approach to doing things. Another possible advantage of the embedded model in a spreadsheet is if you're worried about intellectual capital of sort of the model that you've developed, that you can hide the LINGO model effectively, so that the user can see, ah, yes, it's doing qualitatively what I want it to do, but the user cannot see what the model looks like. So that's an illustration of embedding a LINGO model inside of a spreadsheet. Well, thank you very much for your attention. So we talked about a lot of models here, and I want to point out that you can find most of these models in the models library at www.lindo.com. Simply click on Help, Models Library, Keywords Index, and type in whatever the topic is that of interest to you, and you'll probably see a relevant model either in What's Best or in LINGO. So here's a partial list of what you can see if you go to that models library, ranging from things like academia, acceptance sampling, accounting, to allocation, assembly line balancing, asset liability management, assortment planning, the BAS model for marketing, sales prediction, benchmarking, binary choice, bimatrix games, a lot of different topics there, all the way from A to Z. So thank you very much again.